Alright, so I figured it out a way to prove the Pythagorean theorem using the second fundamental theorem of calculus. So what we want to do is just make a graph with the triangle inscribed into the axes. And hopefully what we can do is find a series of functions, or just find 4 functions that will create the c squared. So obviously this is one of them, extending from the hypotenuse of the triangle. We have one perpendicular to that line and intersects the line at 0, b, and then another one here which intersects the line at a, 0. This one's also perpendicular. And then we have one here which this distance is also c. And hopefully you can notice that this triangle is congruent because like angle, side angle stuff. So this distance would be b and this would be a. But anyhow, if we find the functions that create these lines, we can use definite integrals to find the area of this, which is obviously c squared, but in terms of a and b. Let me use different colors for these lines because this might get confusing. Let's call it the red one f of x. This blue one is g of x. This green one is h of x. And let's do pink. This pink one is I of x. Alright, f of x is perpendicular to I of x. I think I of x is the easiest one to find first because you know that the y-intercept is b and the slope is negative b over a. So this equation would be negative b over ax plus b. Then f of x is perpendicular to that, and the y-intercept is again b, so this is just a over b x plus b. And then h of x it's parallel to f of x, but instead of the y-intercept at b, it has the x-intercept of a, so you can just write that in point slope form. So a over b times x minus a plus 0, which is obviously equal to a over b x minus a squared over b. And then g of x is parallel to I of x. So again, we can use point slope form. Sorry. Negative b over a times. Now we need to find a point on here. And that becomes a little bit tricky. But we know that, remember earlier I said because the triangles are congruent, this distance would be a plus b, and that would just be a. So this point right here, the coordinates are a plus b comma a. So let's write that down. Minus a plus b. So if we distribute the negative sign, it's minus a minus b, and then plus a, which is equal to negative b over a x plus b plus b squared over a plus a. Alright, now that we have four functions, we can write some definite integrals to represent the area of the square, which is, again, that's c squared. So if I take this section right here, we can use one integral for this, and then I don't know, lavender, an integral for this section, and then running out of colors, but you can have an integral for this section right here. Alright, so let's write that out. C squared, the area of the square, is equal to the integral from 0 to b, because recall that this is b, 0 to b of f of x minus I of x. Of course, that's with respect to x. And then the lavender section is integral from b, where the orange section ended, to a, because of course that's a, and then of g of x minus I of x. With respect to x. And then recall that this is a plus b. So the final integral, the kind of toothpaste green section, would be integral from a to a plus b. I left something here. A plus b of g of x minus h of x. Oops, that was the eraser. A plus b of g of x minus h of x with respect to x. So I'll just underline these because I forgot to write them in different colors. Wait, this color. Alright, and that's equal to, I'm gonna expand some of these integrals just to make it easier. 0 to b of f of x dx minus integral from 0 to b of I of x dx plus integral from b to a of g of x dx minus integral from b to a of I of x dx plus integral from a to a plus b of g of x dx minus integral from a to a plus b of h of x dx. And then you'll notice that we can combine some of these. Like, we have the I of x is going from 0 to a, but negative, of course. So we have the f of x minus integral from 0 to a of I of x dx plus the g of x's we can also combine to make b to a plus b. G of x minus integral from a to a plus b of h of x dx. And hopefully if we do this right, the integrals will evaluate to a squared plus b squared. Alright, let's solve some integrals. So this one would be f of x, antiderivative of that would be a over 2b times x squared plus bx from 0 to b. So the calculus here is not hard, it's just power rule. And then I of x is negative b over 2a times x squared plus bx. That's from 0 to a. And then we just do the same thing all the way down. So this one's a little longer. This one's from a to a plus b. Alright, now let's write that out. So these ones from b to 0 and a to 0, that's and when you plug in 0 for those, it's obviously just 0. So can I click this button? Hold up. This would be a over 2b times b squared is just ab over 2. Then that'd be plus b times b is b squared minus 0. And then minus b times a squared. That'd just be negative ab over 2 plus ab. And let's just distribute the negative real quick. That'd be plus AB over 2 plus or minus AB. And you'll see that we already have stuff canceling out. These AB over 2's add up, and then minus AB. And then plus, now for this one, we get, you have to plug in A plus B, so it's a little trickier. Sorry, this should be a minus sign. Minus B over 2A times A plus B squared plus A plus B times B would be AB plus B squared plus B squared over A of A plus B, B squared over A times A, which is B squared, plus, get this, B cubed over A plus A squared plus AB when we distribute that last term. And then minus what you get when you plug B into that. So it'd be plus B cubed over 2A minus B squared minus B cubed over A minus AB. Again, we have some stuff canceling out here. There's a AB right here. Guess I'll get rid of that. B cubed over A. Guess I'll get rid of that. B cubed over 2A. We can get rid of this B squared like that. And I'll just leave it like that for now and go on with the last integral, which was minus, when you plug in A over A plus B to that, it's A over 2B times A plus B, sorry, A plus B squared, and don't forget to distribute the negative there, plus A squared over B times A plus B, which is just A cubed over B plus A squared. And then we subtract what we get when we plug in A, but remember there's this negative sign right here. So distribute the negative, it's plus. So A cubed over 2B minus A cubed over B. Alright, and that's it. Let's cancel this out real quick. Plus A squared. Yeah, so this is equal to, so how many B squareds are there? There's 1, 2, so 2B squared minus this stuff, so B over 2A times A plus B squared plus AB. I think there's just one of that left. And then plus 2a squared because there's one right here and one right here. Minus this stuff, so a over 2b times a plus b squared, and then plus a cubed over 2b. And I forgot the b cubed over 2a, which is right there. Alright, so that's pretty simple. This would expand out to a squared plus 2ab plus b squared, and b over 2a times that would be first let's put these at the front. 2b squared plus ab. I think I can actually factor out a negative a plus b squared. And that's b over 2a plus a over 2b. And if you think about it, that's just, if you combine that into one fraction, that would be b squared plus a squared all over 2ab. So let's do that. And then if you combined these into one fraction, it would be a to the fourth plus b to the fourth over 2ab. And then this a squared plus, or this a plus b squared is a squared plus 2ab plus b squared. So that would turn out to be a squared plus b squared plus 2ab times a squared plus b squared over 2ab. And this is some pretty hard multiplication, so I'm going to use the box method. We have an a squared term, a b squared term, and a 2ab term, and then an a, just for the numerator here, an a squared term and a b squared term. That'd be a to the fourth, a squared b squared, 2a cubed b, a squared b squared, b to the fourth, and 2a b cubed. And then all of that over 2ab. So this would just be eraser. That would be a to the fourth plus b to the fourth plus 2a a squared b squared plus 2a cubed b plus 2ab cubed. And remember that all of this is negative. So what we can do there is subtract all of that from this right here. So the a to the fourth plus b to the fourth, that would cancel out. 2a squared b squared plus 2a cubed b plus 2ab cubed. These 2's would cancel out. The a, get rid of 1 from this term. This would become a squared. This would just become b cubed. B's, this would just be b. And then this would be squared. And remember, all of this is negative. That's pretty messy with all the crosses, but that would just turn out to be negative a plus, or sorry, ab plus a squared plus b squared. So coming back, what we've done is turned this whole thing, this whole section into negative ab plus a squared plus b squared. So let's erase all this stuff at the bottom. No more box method, I'm sorry. Erase all of this. So c squared once again is equal to 2a squared plus 2b squared plus ab minus ab. Distributing the negative, we get minus a squared and minus b squared. The ab's cancel out, and then that's just 2a squared plus 2b squared minus a squared minus b squared. And oh, that is tricky. It's just a squared plus b squared. And all of that is equal to c squared, which is Pythagorean theorem. So yeah, that was a pretty easy way to prove the Pythagorean theorem.